Welcome to the Virtual Scholars Day presentation. Just a little housekeeping before we start. Please make sure your microphone and video are muted and your computer sound is turned on. The Carl Goodson Honors Program hosts OBU's annual Scholars Day, and the event is sponsored by OBU's Alpha Tau Student Honors Organization. Scholars Day focuses on the academic achievements accomplished throughout the school year by students from various disciplines. The presentations and papers are digitally archived on OBU's Scholarly Commons. Today's presentation is by Lee Grisham, who is a senior math major and education minor. Lee, are you ready to share your computer screen?
Yes, ma'am. Okay, can everyone see that?
Yes, it looks good.
So again, with what my presentation is. So I've worked through a few paradoxes, impossible situations, things that make it where certain things we see cannot happen, just through pure logic. So I was introduced to these at a pretty young age, I believe 6 or 7. I was told about the grandfather paradox, where a guy goes back in time and kills his grandfather before his father's ever born. So with this happening, the person can't ever be born and go back to time travel and kill their grandfather in the first place. And so it just begins an endless loop, and you don't know how it can happen or what it really causes. So I looked into this more myself, but it got me started past time travel, which I also really enjoy, into just researching other paradoxes, and just kind of led me on a path to where I love to just think about these pretty much in any spare time I had. So I researched more and more, and it's just great for passing time. It gave me something to do, didn't need anything else. So I didn't have to like go to the store to get something every time I wanted to think about them. And it's just great exercise for the mind. So I'll be using math concepts to solve a few paradoxes today. But these only recently became an idea for me. For pretty much until this past year, I had no idea how to work through any of these paradoxes. And I tried to work through them pretty much once a day almost for any time I was free. I had free time. The idea to use math came while I was a teacher's aide in my Cal 1 class, my calculus class this past semester. If I was thinking about an arrow problem, which we'll go through in a minute. And one of the concepts we've been working on in calculus just popped into my head when I was thinking about it. And I started working and broke down the problem, figured it out. So then I started working on figuring out what had been wrong, like why I hadn't been able to think of these things before. Well, I'd followed the logic of the problem like every time that I thought about these. And if you do that, you're going to get exactly what the original philosopher got that came up with it. And you're just going to go through the same things every time. Definition of insanity, as I was expecting to figure it out using the same methods. So that led me to realize I needed to change my approach. Not solving something one way, you have to try something else. And when I figured out this calculus concept, I began looking at them using mathematics rather than just sequential logic. So the arrow problem is the first one we'll be going through. So it basically begins with, at any moment or instant after an arrow has been shot, it's still, location isn't changing, so it's not moving. The next instant, it must stand spot because it wasn't moving the previous instant. So that means it's not moving. The arrow could not move through the air because each instant it'll be the exact same spot as it was before. So then you move from that to say that it can be applied to all objects. So basically, motion cannot exist as everything will be exactly where it was the previous instant, every instant. So for a solution, when I was working through our Calculus 1 class stuff, I came up with derivatives. Or I didn't come up with them, we were going over them. So it's not really important how you find a derivative is kind of what they are and what they do. It tells the slope of a line at any given point. This can be used for lines that don't have a slope that's equal throughout all of it. So like if a line has a curve or anything like that and the slope changes, you can still find the slope at whatever point you want. So for this, applying to the arrow paradox, we have that in a distance over time graph, your slope is going to be your speed at that instant. So it obviously has some speed at an instant. So you realize that the speed of the arrow isn't actually zero, but can't figure out how we got to that conclusion. So you have to figure out where the problem came from, how it hid that. And that is through the language and a hidden division by zero in the way he sets it up. So he begins with saying the arrow is still because its location isn't changing. The location not changing is not saying that it's actually still, though. It's saying that its location isn't changing at that moment. That is because time has stopped. So unchanging location over time tells you that it's still. Without time, you can't just say that it's still, even if it's in one spot the entire duration. So the hidden division by zero is in an instant, no time passes. Because your speed is distance divided by time, if you say that it's still, you have zero distance over some amount of time. If you say no time passes, you're saying that time is zero. And that would mean your speed is zero distance divided by zero time, which makes it where you can't say that the speed exists, as that would be zero over zero. So in consecutive instances, some time must pass between them, otherwise they're the same instant. So you must have some duration of time that's more than zero. So with instantaneous speed, you can apply that to this time, however short, by breaking it down into whatever distance it is traveled. It's traveled between the two instances you set over the duration of time, and putting it over that time. So with the arrow having to move some little bit over whatever duration of time you have, you realize that it can move, and we've pretty much figured out this paradox. It's just the fact that your instances don't break down time. It's however long you choose to put between them. If you use a durationless instant, then it's not being still. It's just that it's no changing location over no time. So next paradox is Achilles and the tortoise. So it goes like this. There's a race between a tortoise and the legendary hero Achilles. If you give the tortoise a head start, then it leads to some pretty difficult situations through logic. So we start by giving it a head start, of course. The race begins after the tortoise is so far ahead, and you start to see a loop. By the time Achilles gets to where the tortoise began, the tortoise will have gone some distance and still be ahead. So Achilles catches up to where he was. He's now moved a little bit. This repeats again. By the time Achilles gets to where the tortoise got, by the time he got to the first place, the tortoise will have moved some small distance further. This just goes on over and over with Achilles going to the previous location of the tortoise and the tortoise moving some little bit. So basically it just happens over and over again. That gives you the idea that Achilles can never catch the tortoise, as he'll always have a little bit further to go. So the obvious solution to this is just graphing. It shows you exactly when Achilles will catch the tortoise based on how far ahead the tortoise started and how far it will have gone when Achilles finally catches it. It gives you a set specific point, but it doesn't actually break the paradox. It doesn't show where the logic is wrong or how it comes up to its conclusion. For figuring out the solutions paradoxes, we want to know where the problem is and how we can get around it. Not just, this is what actually happens. It's a experiment, not a, this is what happens, obviously. So for the Achilles solution, we use limits, which is basically as you approach a certain input of a problem or of a math problem, your output approaches something else too. like approaches a specific value. It's great as you get close, but not at the moment you reach the point. And even at the point of the limit, like whatever x value you have, you can have your limit, you may not. So how this applies to the Achilles solution. The Achilles solution shows where the paradox hides a limit through its language, and basically gives bounds to how far Achilles can go without outright saying it. So in the language of it, you have that the final event is where Achilles will catch the tortoise. This limits the maximum distance and the time that Achilles and the tortoise have been racing. It basically makes the end point where the tortoise is, and it limits time to the point right where Achilles approaches the tortoise. It makes it seem like this boundary is impossible, or it's one of the limits that cannot be reached. So basically, if you limit time and then put a boundary there, for limits, it's, like I said, it's as you get close to a point, but it doesn't actually take into account the point itself. So this logic is just, the logic of this paradox is completely disregarding the point itself by saying you get closer and closer and closer and just breaking it down to smaller and smaller pieces as you reach the point. So we'll look at a few graphs and I'll explain the difference. This is the actual graph of the race, with the blue line being the tortoise and the red line being Achilles. So if you see, this is the real one. They meet up at this point, about 8:16 on the graph, 8 seconds with 16 meters travel. The second graph is what the problem breaks it down into. You see a giant hole right where they would meet. So when you take the limit, it starts breaking down. Like at first, it'll say that they would meet. They would be almost meeting. You see that Achilles reaches the point where the tortoise started here at 4:08, and the tortoise has now moved about 12 meters into the race. Then it just breaks down time into further smaller points, and you see that Achilles is getting closer, not reaching it. So after you get to about 7:15, you see that it's obviously getting a lot closer. So it basically, between that and the point where they would meet, breaks it down infinitely and just keeps, it doesn't actually allow you to get to the 8 seconds required for Achilles to catch the tortoise by just breaking it down further and further. So because it hides that hole and only keeps breaking it down, Achilles actually catches the tortoise because you can't break down time infinitely. That gives you 0 time again. And you realize that Achilles eventually catches the tortoise. It's just the hidden limit along with breaking it down time over and over instead of allowing time to progress. So the last paradox we'll be going through today is the dichotomy. It's also known as the racetrack paradox. So Atlanta wants to take a walk to the end of the path. Before reaching the end of that path, she has to go halfway. For that, she has to go halfway of halfway, and so on and so on. And it basically says that because she can never get to each distance because there's always some shorter distance she has to walk, she can never reach the end of the path, and goes on to say that there is no first distance, so she can never actually begin her walk. So this kind of takes elements from both the arrow problem and the Achilles and the tortoise problem by limiting distance and breaking it down so that motion cannot exist. So again, this one uses limits just like the Achilles paradox did, but it uses them in a different way. So the similarities to the Achilles paradox is, of course, that it uses hidden limits and it breaks down distance infinitely. So the difference is that whereas in the Achilles paradox, we had a maximum limit in the time and distance traveled, in this one we have a minimum limit. It's basically saying no distance can be traveled, limiting it to 0. And then the Achilles paradox, there was a reachable limit, whereas this one, it's unreachable. Like this limit actually cannot exist once you begin. And then in the Achilles paradox, we were trying to show an ending point, whereas in this one, we have to show the starting point that it can begin. So we have a different approach still using the limits. The minimum limit cannot be reached, and we're going to go through how the starting point has this, and we're going to see the other mathematical steps involved. So with the minimum limit, it basically hides it in the starting point. Because there is a set starting point, on a graph, this would be the origin 0, 0. The minimum limit for distance traveled is 0. We know there's some velocity from walking, so your speed will be greater than 0 as well. Immediately after time has started, Atalanta will have moved from the starting point. So the other mathematical steps that go to this. When it's breaking it down from the full distance to half of that, and so on, it's splitting the distance infinitely. This is actually also infinitely splitting time. For limits, this would say that the limit as distance or time approaches 0 will give you a distance of time or 0 over and over. So basically, your mathematical equation for that, or expression for that, would be 0 over 0, which again, I said earlier, we cannot do. That would give us a division by 0. We have to take the distance over an interval of time. So our interval has to be greater than 0 because of that. And so our limit of 0 time can never be reached. What that does means that we have to take the interval of time, and that gives us an interval of distance. Because of our velocity being greater than 0, if we have a time of anything greater than 0, our distance will also be positive and have some magnitude. With the magnitude of distance, that means we will have traveled somewhere. And if you want to break that down into parts so that she eventually reaches the end, you just multiply the distance and time by some number, and that'll eventually give you the full distance walked. So with the limit being 0, you realize you can't actually reach that limit. The wording, if we go back to it, says that she won't go anywhere, but that's just because it's breaking down time infinitely. And like, as you have one small part of the section, if you keep breaking that down infinitely, you'll always have some little bit. Because it breaks that down infinitely, it makes it seem like it goes down to 0, but that's just because it's dividing time into parts of 0 magnitude as well. So basically, here we go. Atalanta will eventually make progress by some amount based on how fast she's walking. You can't just disregard the velocity by saying that she never starts, because that's basically just taking the point where she begins without taking into account her motion at all. That is the whole presentation. Okay, any questions?
Any other questions for Lee? So Lee, which of these are your favorite paradoxes? Which one of these is your favorite?
So for me, that would probably be the Achilles and the tortoise paradox. It was actually, took me a little bit to figure out that it was just breaking it down into a limit to solve it, and probably took me the longest out of the 3. But because there was so much that went into it, it was probably the one I had the most fun thinking about and figuring out. Overall, my favorite paradox would probably be the grandfather paradox I spoke about earlier. That one, I don't see a way to figure out yet. So it just takes time travel being invented to figure out. It's just really interesting to me.
Any other questions for Lee? Well, thank you very much, Lee, for a great presentation. And thank you to our viewers for watching today. To see this presentation and other works by students, you can visit scholarlycommons.obu.edu. Thank you very much and have a great afternoon.
Thank you.